welcome to another tutorial. My name is Tammy Bakshi, and this time we're going to be going over another math video. And today we're going to be talking about transformations, more specifically rotations. So today I'm going to be covering a lot of different types of transformations, 4 different types to be specific, but the main one that I'm really going to be going in depth about is going to be rotations. So just before I begin today, let's start off with transformations in general. Now, there are 4 main types of transformations. These are, now I'll get into each one in just a second and what they mean, but let me actually just begin with transformations. There are 4 main types. There are translations, stretches and compresses, or stretch and compression. We also have reflection, and of course rotation. Now, the main reason that I'm talking really about rotations today is going to be because, well, I find that a lot of people have quite some difficulty with rotations, and I really want to help as many people as I can. So I'm going to be covering the most complicated topic out of them all, which would be rotations. So let's actually get right into this today. As you can see, I have a few coordinate spaces drawn out here. And so today, before I begin with rotations though, I'm going to be talking about lots of other types of transformations in general. So let's actually begin with one of the simplest types of transformations, translations. Now, translations are very simple. So if I just say, so first of all, we're going to be talking about translations. Okay, so let's actually begin. Now, quite simply, let's say we have a shape. Okay, we've got a shape over here on our coordinate space. And let's just say we wanted to translate it. Well, quite simply, all we do is move the shape. We're not going to manipulate the shape whatsoever, but we can move it left, we can move it right, we can move it up, and we can also move it down. Now, again, we're not manipulating the shape or anything, we are just moving it around this coordinate space, and that would be a translation. And this can go left, right, up, or down. And remember, you can even move it diagonally, indirectly, by going, let's say you wanted to move in this direction over here, you'd go left and then up, or you could go right and then down, or really however else you'd like to move. Essentially, we're just moving the shape, which allows us to translate it. Okay, so that's what translations are, quite simply. So I'm not going to be covering that in too much detail in this video, but then again, if I do get enough response that, you know, people want to learn much more about rotations, that'll be coming in another video. But now let's talk about stretch and compression. So of course, our next topic is stretch. Oh, sorry. So we're going to be talking about stretch and compression. In this case, both vertical and horizontal stretch and compression. Okay, so we've got stretch and compression here. And so let's just say, you know what, the best way to explain this would be, let's say we have a curve. Okay, I'm going to draw a nice big curve over here. Okay, so we've got this nice black curve. And I'm going to say this is our O curve, meaning original curve. Let's take a different color, maybe blue, I guess. So we've got our blue marker, and let's just say that we want to stretch this curve vertically. How would we do that? Well, seems a little weird at first, but think about this. This would be our stretched curve. This is what would happen if we were to stretch a curve vertically. Okay, so this is our S curve. Now, you must be wondering though, how does this work? This is obviously compression. Well, no. Imagine this. We've got a curve. And let's say we were to take this curve, grab it from the top and the bottom vertically. We were to grab it vertically and stretch it out vertically. The top goes even higher and the bottom goes down. Then, of course, from the sides it would get thinner and thinner and thinner the more I were to stretch it vertically. That means horizontally we would be compressing it, but vertically we would be stretching it. And so that's what we're doing in this case. We're taking our curve and we're taking it and we're stretching it from vertically. And we end up with this nice horizontally compressed, vertically stretched blue curve. Now, the exact same concept applies to compressing vertically. So if I were to take something of this sort, so if I were to just take like this red marker and this isn't exact, unfortunately, because, I mean, of course, I'm not a computer, I can't get it perfect. However, this is a quite close imagination of how this curve would look compressed. So, again, the way we're doing this is imagine we have our curve again, and we take it from both the top and the bottom, vertically, and we compress it vertically. Of course, the sides will get stretched out, and so this is a horizontal stretch, but vertically, we are compressing this red curve. We're compressing this black curve, this O curve, in order to get the red final compressed curve. Alright, so now let's actually try something else. So before I get into rotations now. We're going to be talking about rotations in a second, but let's talk a little bit about, well, reflections. So, alright, so reflections, what are they? Well, you know what, this is best explained with an example. So let's take an example. Let's say I were to draw a little triangle here. Okay, if I were to just finish this up. So now we've got ourselves a nice little triangle. And so it's more towards the right than it is up. So it has more of an x value than it does a y value. And so let's say we wanted to reflect this on the x-axis of our coordinate space. All we do is negate the y value. Sounds weird because this is our x value right over here. This is our horizontal x value. And so what we have to do is negate the y value in order to get our reflected shape or point. And so in this case, let's just say I were to roughly calculate here, we would end up with something around here, and then here, and then like this. This is what would happen if we were to reflect. And technically, if I had a piece of paper, and if I were to do it on a piece of paper, and if I were to fold the paper in half along this x-axis, then these two should be perfectly symmetrical. This should be able to overlap right on this perfectly, if I've reflected it nicely. However, if it's even a bit off, it shouldn't. But technically, a reflection would be completely symmetrical on that axis. And then again, the same concept applies to this y vertical axis we've got here. So what we would do is, let's say we wanted to reflect this on our y vertical axis. Quite simply, all we need to do is, of course, take this axis and of course, with the x-axis, in order to reflect on that, we negate the y value. So in order to reflect on the y-axis, we negate the x value. And so, of course, all we need to do, negate the x value, and let's say just approximate this here, it would end up around somewhere here-ish. So, again, not perfect, but this is around where it would end up if I were to reflect on the y-axis. And again, if this was paper and not a solid whiteboard, then I could just, fold this in half, and I should be able to see this overlap perfectly onto this, our original shape, or our original point, and it should be perfectly symmetrical. Of course, though, I'm not a machine, so I wouldn't be able to do that. But now, I'd like to get into the main reason of why I'm creating this video today: rotations. And so without any further ado, let's get right into rotations. So let's begin. Now, again, another thing I'm going to be doing today is actually going to be able to show you not just how you can, use those classic old methods of rotating your notebook around and doing all that sort of stuff. Instead, I'm going to be introducing you to a generic algorithm that'll allow you to calculate the coordinates of how you could rotate a shape counterclockwise or clockwise, not just about the origin, but another point, which I will get to in just a second. So now, before we begin, I have to show you something. So, of course, we know what the origin of our coordinate space is. The origin would be right over here, okay? And the origin is our 0, 0 point, okay? Now, this is our origin, okay? We agree this is the very center of our coordinate space. And let's just say I were to draw a rectangle or square, or really any shape, or even a point on this coordinate space. Now let's just say, and actually in order to help me do this, I'm going to use my trusty string. So this is going to help me rotate. And so again, this is one of those classic methods, right? Using one of these strings, or a compass, or rotating a notebook, or the wax paper. But today I'm going to be showing you how you can actually calculate those coordinates. But what I'm going to be showing you on the whiteboard here today is just generally that this is a rotation. If I were to take my marker, say, okay, let's say this point we want to rotate. Now let's say we want to go counterclockwise about the origin. Quite simply, that's all we need to do. And now this is how we can go counterclockwise over in this direction. That's how we can rotate counterclockwise about our origin. However, if I wanted to rotate clockwise, almost the same drill. We just take that little origin again. I'm just going to put that on the origin, and then that would be how we rotate clockwise about the origin. Now, that's quite simple, but it's not fun, right? And so, of course, I'm going to be showing you how you can just take those coordinates and calculate how to rotate it 90 degrees clockwise or counterclockwise. However, something else very, very interesting that I'm going to be getting into in just a second is, let's say we were to have another point over here and we were to label this point B. Okay, now this is a point in our coordinate space. What if we wanted to rotate this same shape or point or anything about point B, but not the origin? And so, if we wanted to rotate clockwise, what would we do? Well, I'm probably going to have to cover this, just give me a second. Well, I'm just going to, again, use my string, and this is one of those old classic methods. I'm just going to do this. And so this is how we would go clockwise if we wanted to rotate about point B, right? And we're not rotating about the origin. And if I wanted to go counterclockwise, and it's, again, almost the exact same thing. All I do is put the marker there, take my string over to point B, and then go over here, okay? So we have to keep going in that direction. And so, of course, today I'm going to be showing you how you can rotate both clockwise and counterclockwise about the origin and a point about another point, in this case, point B, on your coordinate space. And you'll be able to rotate anything, a shape, a point, anything. And so, of course, I'm very excited to get into a more detailed explanation of rotations themselves. Anyway, though, thank you for watching this whiteboard part. Let's get right back into an actual in-depth explanation of rotations themselves. Let's get to it, shall we? Alright, so welcome back to this explanation part now, and again, we're talking about transformations, and again, in this video specifically, I'm talking about rotations. But if this video gets a lot of, support and people like it, and people want to know more about it, of course, I will create more tutorials on many different topics in transformations, the translations, the stretching and compression, our reflections, that type of stuff. I'll be creating videos about all that sort of stuff. If this video gets, a lot of support and people actually want to know more about this topic. But anyway, let's begin. So now, as you can see in front of you, I've drawn a grid. Now, in order to show you what a rotation would be on a coordinate, space or coordinate, one of those coordinate spaces, we need to draw that out. So let's actually draw out one of these coordinate spaces. All right. So as you can see, we've got 4 quadrants, and we've got our positive y, our negative x, and our positive x. And each one has their own quadrants. And so let's actually label the origin. of this coordinate space, which is 0, 0 in the middle, just in between everything, very middle of everything. And let's mark a point on this coordinate space, which is 6, 2. All right, so this is a 6, 2 position, 6x, 2y. So we are essentially moving 6 in as x, 6 towards the right, and 2 up as positive 2y. Okay, now let's say we wanted to rotate this 90 degrees clockwise. How would we do that? Well, I'm going to give you a quick sneak peek into the future, and I'm just going to give you the answer right now. The answer is 2, negative 6. Okay, we rotate 6, 2, 90 degrees clockwise, we're getting to 2, negative 6. But how? How is that possible? Well, let me show you. Let's draw a line with 0y, with 0y, but 6x, so we're drawing a 6, 0 line. This is a blue line, and as you can see, if we have, as you can see, all of these quadrants that we have here, these 4 quadrants are at right angles. And so if we were to rotate this blue line 90 degrees clockwise quite easily, we could say that it would end up here. But this still doesn't really prove how we could have 6, 2 rotated 90 degrees clockwise to 2, negative 6. How does that work? Well, let's put this line back. And let's draw a latch from 6, 2 to this line, another blue line. And now let's rotate this line 90 degrees clockwise. And as you can see, it ends up at 2, negative 6. In fact, in order to prove that this is 90 degrees, we can actually draw lines between them, and as you can see, the angle here is 90 degrees. So it has been proven that we have actually rotated this 90 degrees. But actually, let's continue this. Right, let's say we were to again draw this line and put a latch to 2, negative 6. Let's rotate this another 90 degrees clockwise, all right? We get to negative 6, negative 2. Now again, we can draw this line and we can see that we have a 90-degree rotation. And we can do this once more and we get to negative 2, 6. Again, we can draw this line and we see that's another 90 degrees. But this is 270 degrees, of course. We went from 6, 2, that's 190 degrees, then we've got 180 degrees, then we rotated 270 degrees from 6, 2 to negative 2, 6 clockwise. And so, after 270, in order to get to 360, so a 360 degree rotation is a full circle. We know that. So if we were to have 6, 2 and we were to have a 360 degree rotation from 6, 2 clockwise or even counterclockwise, we would reach back at 6, 2. And after 270, we get immediately, if we add another 90, 360. And so, in theory, if this blue line hits 6, 2 again, that means that we have actually rotated 360 degrees and that we have actually rotated 90 degrees every single time. And so, as you can see, it does. And if we draw this line, you can see that indeed we have been rotating 90 degrees clockwise every single time. We went from 6, 2 to 2, negative 6 to 6, negative 6, negative 2 to negative 2, 6, and then 360 degrees back again to 6, 2. And this was all done in a clockwise way. But okay, so this is great, but how would this really help us? This is no different than, as I was saying, those classic techniques. We need an algorithm or some sort of pattern. So let's actually take a look at what this pattern is. So as you can see, pattern. We began with positive 6, positive 2. Now, in order to get to the next rotation, the next 90-degree clockwise rotation, what we need to do is, first of all, we have to have a negator, okay? And we also have to have, what we're going to do essentially is we're going to swap. As you can see, we went from 6, 2 to 2, negative 6, and so we're going to swap the 6 and the 2. But what we're also going to do is we're going to make it so that while the 6, the x value, is moving into the y value, into the y position, we're going to negate it to make it a negative 6. And so the positive 2 over there, the y value that's going into x, that remains intact. The sign remains intact. However, the positive 6 that goes into the y value, that's currently x that goes into y, gets negated to negative 6. And we end up with our coordinate. Now, another thing I'd actually like to draw your attention to is just before we continue with our pattern, if you take a look over here, we have 6, 2, and we have negative 6, negative 2. Now, these two coordinates, what's happening is when you have when we have 6, 2, which is in one of the quadrants, if we were to move it diagonally, if we were to reflect, remember when I explained reflections in the beginning, if we were to reflect it exactly diagonally to its diagonal quadrant, we would have it exactly placed diagonally. And as you can see, if we just negate the 6 and the 2, we have negative 6, negative 2, and it's placed perfectly at a 180-degree angle from clockwise or counterclockwise, anyway, from 6, 2. And that proves, again, that we've been rotating 90 degrees every single time. But continuing with the pattern, though. So now we've got positive 2, negative 6. Let's see if the same pattern that we applied to positive 6, positive 2 applies to this as well. So let's say we swap and negate the x value while it's going to y. As you can see, we end up with negative 6, negative 2, because the negative 6 value, its sign stays intact while going over to x. However, the positive 2 gets negated while going over to y, and we end up with negative 6, negative 2, which puts us at a 180-degree angle with that other quadrant over there, which is a 90-degree turn, which is a 90-degree rotate, however, from positive to negative 6. Now again, we put the same pattern into play. We have the y value going to x, sign stays intact, the x going to y, it gets negated, and we end up with negative 2, positive 6. Because, of course, negative 6 negated would be positive 6. So, now, continuing though, let's say we were to put this again. Now, as you can see with negative 2, 6, we've done, as I said, a whole 270 degrees of rotating. And if this pattern continues again with 2, 6, negative 2, 6, sorry, and we're able to get 6, 2, that means we've done a full 360-degree rotation, and every single time we rotated 90 degrees. So let's see. Positive 6 will remain intact while going over to x from y. But the negative 2 will get negated to positive 2 while going over to the y value, and we end up with positive 6, positive 2. And we have made a full 360-degree rotation with this pattern, which proves that it actually does work. Now let's actually take a look at the algorithm though. Sure, we've gotten a pattern, but what's our final algorithm of how we can actually rotate a point 90 degrees from the origin? Well, it's as simple as this. We have our original starting point, let's say positive 6, positive 2, or positive x and positive y values. We essentially have the x going over to the y spot and getting negated, whereas the y goes over to the x spot while keeping its sign intact. And we end up with positive y, negative x, because the negative x was negated. Now, you must be wondering though, sure, we can, apply this to points, but what about shapes? How can we rotate shapes from the origin? Well, let's put this simply. All you need to do is, let's say you have a triangle with points A, B, and C. Well, what you do is exactly that. You'd label those points, and you'd find their positions in the grid. What you do is you'd actually rotate each point individually using this algorithm. Once you've done that, and once you've labeled those rotated points, you're going to connect those points just like you would for creating the shape. And of course, you have your shape that has been rotated 90 degrees clockwise. Alright, so that's the algorithm for this, but this is nice and all. We're rotating from the origin, but let's say we want something more complex, more fun. Well, what if we wanted to rotate from a point that's not the origin? Sounds weird, doesn't it? But let me explain. So we have this blank grid here again, this blank coordinate space. And we have our origin labeled as 0, 0. And we have a red dot that we want to rotate. We're going to label this as 1315 because that's its position on the grid. That is relative to the origin. But now let's say we have a black dot. Okay, and we label this black dot 912, which is its position relative to the origin. And we wanted to rotate this red dot not from the origin, but about this black dot. How would we do it? Well, first of all, let's begin by drawing a circle, and let's talk about the algorithm. Let's dive right in. So to begin, we have 1315. Now, again, we are not rotating about or relative to the origin. That's supposed to be about the black dot. And so, in order to do that, we need to find the red dot's position with respect to that black dot in 912. And so, what we do is we subtract that 912 value from 1315. And this results in 4, 3, positive 4, positive 3. And this is our final value, which is actually, 1315's position according or sort of in respect to the 912 dot. And so what this means is, of course, the 4x, 3y. And so this means that we're going 4 to the right and 3 up. That is our position. That is the red dot's position like relative to that black dot. And so what we can do now is use our classic algorithm that we're so used to. We can swap these values and negate the x going to the y, and we end up with positive 3, negative 4. But wait a minute. We have our algorithm output that we've been using for so long now. But this is not the value of 1315 rotated 90 degrees clockwise. Remember how we factored in, or we found 1315's location relative to that black dot? Well, yeah, we encoded that, so I guess you could say encoded. It's not technically encoding, but quote unquote, if you will, we have encoded 1315 with that 912 location. And we got 4, 3. And so now we need to take this location that we've got, this coordinate pair, and decode it. And we're going to put this on the side, okay, so we don't mess up our current coordinate pair. And in order to decode it, well, quite simply, we just add back the 9 and 12. This results in 1208. And in order to prove to you that 1208 is in fact that 90 degrees that we've rotated from 1315 about the point 912, well, let's put that on the grid, and let's label it. As you can see, that is our 1208 point. And that is how we were able to rotate 1315 90 degrees clockwise about the 912 or black dot point instead of the origin. That's pretty interesting, but let's say we wanted to continue. We've done 90 degrees, but let's do 180 degrees, which is 12/8 but another 90 degrees clockwise. How do we do that? Well, again, we're using the same positive 3, negative 4 value that we got from our algorithm, and we're going to run the same classic algorithm again. The y value going to x will stay the same, not stay the same, the sign will stay intact, whereas the x value going to the y will be negated. And finally, we get negative 4, negative 3. But again, we need to decode it. And so what we do is we bring it to the side, we add 912, and we end up with 509. And using this value, we can put that on the grid, label it, and as you can see, that is indeed 90 degrees clockwise from 12/8 and 180 degrees from clockwise from 1315. And then again, that is about the point 912 and not from the origin. Let's actually continue this pattern once more, and we end up again with negative 3, 4. If we take this to the side again, decode it with the 9 and 12, and we end up with 6, 16. We put that on the graph, and we label it. And as you can see, we have that 90 degree turn again. So now what we've done is we have a 90 degree clockwise turn from 5, 9, about the point 912, which is 6, 16, But it's a 180-degree rotation from 12.8, and it's a 270-degree rotation from 13.15. And so, again, we apply the same algorithm as we did last time. If we can take 616 and apply our same algorithm in order to rotate it 90 degrees clockwise, that would mean from 1315 it should be 360 degrees. And since 360 degrees is a perfect circle, that means we should end up with 1315. And so we run our algorithm again. The positive 04 sign stays intact and it goes from y to x. And negative 03 sign gets negated to 3 and goes over to y. And as you can see, we end up with positive 4, positive 3. And that is the same value we got when we took positive 13, positive 15, minus positive 9, positive 12. We got 4, 3, and now we got 4, 3 again. And so there's no doubt that if we take it to the side, add 9, 12 again, we get 13, 15 as our final result. And as you can see, we have rotated 13, 15, 360 degrees clockwise, about the point 9, 12, not the origin. Now, this is pretty nice, isn't it? How we were able to take something that was so frustrating and simplify it down into one algorithm. But we're not quite done yet. There's still one more step. What if we wanted to take all of this and we wanted to condense it into one final algorithm? How would we do it? Well, let's say we have two different algorithms. One to rotate a point clockwise and one to rotate a point counterclockwise. Let's begin describing how this would work. Well, again, this isn't going to be about the origin. It could be about any point. It could be about the origin. It could be about another point, really anything. And so we have this red dot that we want to rotate. Okay, and we're going to say its location is xp, yp. That is the red dot's location, and this is what we want to rotate. And this is one of the inputs that both of our algorithms will take. But then we also label the black dot, and this black dot is what we want to rotate about. Now this black dot could be the origin, it could be where the black dot currently is, it could be any place or any location on this coordinate space. And we're going to label this black dot as XO and YO. Then what we're going to do is we're going to take this black dot, and what we're going to do is, again, just like we did just a few seconds ago, we're going to take XP and YP, and we're going to subtract XO and YO from XP and YP, just like we did, as I said a few seconds ago, and this is going to happen in both of the algorithms, and we're going to end up with a result that I'd like to call X1 and Y1. And this is where the algorithms start to differ a bit. And so what's going to happen is, let's just put our negators here. And so just like last time, again, what I'm saying is we're using the same algorithm. We are essentially, for the clockwise one at least, we're taking x1 and we're putting it into the y's position while negating it. So the positive x1 becomes a negative x1. Whereas the positive y1 switches over with the x's position while keeping its sign intact. However, on the counterclockwise side, now, I mean, you've already seen the clockwise side, that's you're pretty familiar with that, but let's talk about counterclockwise. On the counterclockwise side, we were essentially able to take the positive y1 value, and we're essentially doing the exact opposite thing that we would do for clockwise. We're taking the positive x1, and we're swapping it with the y position, alright? We're doing that, but we're not negating. We're keeping its sign intact. Whereas we're taking the positive y1 and we are, of course, swapping it out with the x position and negating that instead. So we end up with negative y1 and positive x1. And so finally, as you can see, we're doing the exact opposite thing for the counterclockwise algorithm than we are for the clockwise algorithm. And this allows us to end up with our result. Now again, we have actually found the location of the 90-degree rotated point, this red dot, 90 degrees rotated. We found its location, clockwise or counterclockwise, but this isn't our final location. But why? Well, again, I mean, you should probably remember this. It's because we did not yet decode it. Because of course, we found the red dot's location in with respect to that black dot. And so now what we need to do is make it back in respect to that middle point, that origin. And so what we need to do is we need to add XO and YO back to our result. And we should finally get an XA value, a YA value for our clockwise algorithm, and an XB value and a YB value from our counterclockwise algorithm. And so, of course, from our clockwise algorithm, as I said, we get that XA and YA, which is our final 90 degrees clockwise rotated algorithm or point. And, of course, from the counterclockwise algorithm, we get XB and YB, which is the final point of where which is the final point of our 90 degrees counterclockwise rotation. And that was all there was to this video. Of course, I really hope you enjoyed and learned a lot. If you did, please make sure to leave a like on this video. It really does help out a lot. And if you think this could help anybody else, please do consider sharing the video. Again, it really does help out. And of course, if you have any more questions, suggestions, or concerns, that type of thing, you can leave it down in the comments below. You can, of course, email it to me at tadgymanny@gmail.com or just straight tweet it to me at tadgymanny. Of course, my contact info will be in the description. But if you really do like my content and you want to see a lot more of it, please do consider subscribing to my YouTube channel, as it really does help out a lot. Again though, finally, I really hope you enjoyed. Thank you very much for watching the video. Goodbye.